Hi, welcome back. Assalamualaikum warahmatullahi wabarakatuh. The second part of Chapter 7, Ionic Equilibria, is Lesson 37, the strength of acids and bases. We are going to calculate the pH and pOH, but before that, we need to define strong acid, strong base, weak acid, weak base, and their relationship with Kw, the autoionization of water. And then we need to relate the strength of a weak acid and a weak base to the respective dissociation constant Ka and Kb. Later, we have to perform calculations using pH, dissociation constant, initial concentration, equilibrium concentration, and degree of dissociation. Before we learn how to calculate the pH and pOH of acid and base, we need to learn about autoionization of water because water does affect the pH scale. So when water molecule autoionizes, it transfers a proton from one water molecule to another water molecule to produce a hydroxonium ion H3O+ and hydroxide ion OH- as shown in the slide. Since the water molecules are in liquid form, if we want to find the Kc for this equation, we're going to have only H3O+ and OH-. The Kc for water is known as Kw because this is the ionization constant for autoionization of water, and it has a constant value which is 1 times 10 to the power of negative 14 molar square. The hydrogen ion H+ concentration in a solution is measured using the pH scale method. pH is defined as the negative logarithm log of the hydrogen ion H+ or H3O+ concentration. The higher the concentration of H+ or H3O+, the lower is the pH value. For base, concentration of OH- is measured using pOH. pOH is defined as the negative logarithm log of the hydroxide ion. The higher the concentration of OH-, the higher is the pH value. In pure water, the concentration of hydroxonium ion is equal to the concentration of hydroxide ion, which is 1 times 10 to the power of negative 7 molar. So if we calculate the pH, negative log 10 to the power of negative 7, it is equals to 7. The pH of pure water is 7. And as we have done previously, the water self-ionization constant expression Kw is equals to the concentration of hydroxonium ion multiplied by the concentration of hydroxide ion, which is equals to 1 times 10 to the power of negative 14. Now, what if we multiply negative logarithm to both sides of the Kw equation? Negative log Kw equals to negative log concentration of H3O+ minus log or concentration of OH-. Now we got pKw equals to pH plus pOH. So at 25 degrees Celsius, Kw is 1 times 10 to the power of negative 14 molar square. This is equals to pKw equals to 14. Therefore, 14 is equals to pH plus pOH. Whenever we got pOH, we can deduct it from 14 to get pH. Ka is the dissociation constant for an acid, while Kb is the dissociation constant for a base. Relationship between Ka and Kb can be explained by using the dissociation of ammonium ion as shown in the slides, where we have two balance equations here. For the first valence equation, we have ammonium ion dissociate to become ammonia, NH+. So the Kc or Ka that we got is the concentration of ammonia times concentration of H plus divided by concentration of ammonium ion. And the second valence equation is the ammonia react with liquid H2O to dissociate and become NH4 plus with OH minus. So we get the Kc or Kb for the second valence equation as concentration of NH4 plus times concentration of OH minus divided by concentration of NH3. Let's put them together, Ka multiply Kb, and both expression of Ka and Kb together, we are able to cross out the NH3 concentration and then NH4 concentration. So what do we have left? The concentration of H plus multiplied by the concentration of OH minus. Here it is Kw. Therefore, we found out here that the relationship between Ka multiplied by Kb is equals to Kw. The strength of acids and bases can be compared in terms of degree of dissociation alpha and dissociation constant K. Degree of dissociation alpha is a fraction or the percentage of molecules that dissociate. It depends on the ability of acids and bases to ionize or dissociate in aqueous solution. The formula to calculate the degree of dissociation for acids and bases is change in concentration of acid or base dissociated over initial concentration of acid or base multiplied by 100%. Example 7.5. The amount of H plus dissociated in a solution of 0.1 molar acetic acid is 1.3 times 10 to the power of negative 3 molar. So how do we calculate the degree of dissociation of this acid? First, we find the change in concentration of the H plus. It's given in the first sentence, 1.3 times 10 to the power of negative 3. And it is divided by the initial concentration of the acid, given 0.1 molar. So we put them in the formula, and the percent dissociation is 1.3%. Dissociation constant K for acid is Ka, and for base is Kb. The pKa or pKb is defined as the negative logarithm log of the Ka or Kb. The higher the value of Ka, the lower the pKa, thus the stronger the acid. And the higher the value of Kb, the lower the pKb, thus the stronger the base. For weak acid, the higher the Ka, the lower the pKa will be, therefore the stronger is the acid. For weak base, the higher the Kb, the lower the pKb will be, therefore the stronger the base. In general, the higher Ka and Kb, the lower the pKa and pKb will be, so the weak acid and the weak base would be stronger. Let's take note that strong acid and strong base are strong electrolyte, whereby the alpha is equals to 100% dissociation. But for weak acid and weak base, they are weak electrolyte because the alpha is very less than 1. Electrolyte is substance that can conduct electricity in the liquid state or an aqueous solution. What are strong acids and strong bases? Strong acid and strong bases ionize completely in aqueous solution. The degree of dissociation alpha is equals to 1 or 100%. Unless the acid or base solution is extremely dilute, the concentration of hydroxonium ion or the concentration of hydroxide ion, which come from the dissociation of water, is excluded in the calculation of the pH of the solution. Here is an example of a strong acid and a strong base. Nitric acid dissociate completely, so it uses the one-way arrow to become hydroxonium ion and nitrate ion, whereas sodium hydroxide dissociate completely and also use the one-way arrow to produce Na plus and OH minus. In strong acids and bases, the hydroxonium ion or hydroxide ion concentration can be obtained from the original concentration of the acid or base used. For example, if we have 0.1 molar concentration of HCl, the concentration of H plus coming from it would be also 0.5 molar. Same as sodium hydroxide, it dissociates completely, so it is going to have 0.1 molar, the same as the original solution. But for sulfuric acid, for 1 molecule of sulfuric acid, it would dissociate to produce 2 moles of H plus. Therefore, if we have 0.2 molar of sulfuric acid, we're going to have 0.4 molar of H plus ion. Okay, let's do example 7.7, question number 1. We are going to find the pH for all these 4 solutions. We know that the formula to find pH is negative log concentration of H plus. So this is the formula we're going to use for all of this solution. For the first solution, we are given the concentration of H plus is 0.035. So pH is equals to negative log 0.035 because this is the concentration of the H plus. So you press your calculator and then you're going to get 1.46 put at 2 decimal places. It's not that difficult, isn't it? Next, let's do example 2. Here we have an acid solution. HCl is a strong acid, so it's going to dissociate completely to release H plus and Cl minus. So the concentration of this H plus is 2 times 10 to the power of negative 3. So we're going to do pH equals to negative log to the concentration of H plus negative 3, and when you press the calculator, you're going to get 2.699, and this is nearer to 2.70. Make it at 2 decimal places. Now, let's look at the sodium hydroxide. Sodium hydroxide dissociate to release Na plus and OH minus. So we are going to find the concentration of OH minus to get the POH. So this is 1 mole, this is 1 mole, this is 1 mole. Therefore, the OH minus is the same as this concentration of sodium hydroxide. So POH equals to negative log concentration of 5.4 times 10 to the power of negative 9. This is the concentration of OH. The concentration of OH here, not H plus. So we're going to get POH equals to press your calculator and you get 8.27. Now this is not pH yet. pH is equals to 14 minus pOH. So we're going to get 14 minus 8.27, which is 5.73. This is the final answer. Oh, I need a new page for the fourth question. Okay, let's look at question D. Question D is about sulfuric acid. So we're going to look at the equation to dissociate this sulfuric acid, which is a strong acid. So it dissociates completely to become this. And you notice that 1 mole of sulfuric acid will produce 2 moles of H+. Therefore, if you have 0.05 molar of sulfuric acid, you're going to get 0.1 molar of H+ concentration. Therefore, we're going to use our pH formula, negative log H+, and this is negative log 0.1. The pH now is 1. Question 2. What is the concentration of sodium hydroxide solution with pH 10.5? First, we need to find pOH because we want to find the concentration of OH minus. So pOH equals to 14 minus pH, whereby pH is 10.5, and we will get 14 minus 10.5, that is 3.5. pOH is equals to, what is the formula? Negative log OH minus. This is equals to 3.5, right? How are we going to get OH minus? So OH minus is equals to 10 exponential negative 3.5. So press your calculator and you're going to get 3.16 times 10 to the power of negative 4 molar. What happened when we dissociate NaOH? It's going to dissociate completely to become Na plus and OH minus. So we are going to have the concentration of 1 mole of OH is the same as 1 mole of sodium hydroxide. This is the stoichiometric coefficient for the valence equation of the dissociation of sodium hydroxide. Therefore, we know that the concentration of NaOH is the same as the concentration of the OH minus. Okay, that's your answer. Question 3 has a long way to go. First, we find the dissociation reaction of calcium hydroxide. It will produce calcium ion, Ca2+, and 2 of the OH minus. So the balance equation here shows that for 1 mole of calcium hydroxide, it's going to produce 2 mole of OH minus. But how much OH minus do we have? We find from the pH. So pOH is equals to 14 minus 10.65, that is 3.35, and the OH minus concentration would be 4.47 times 10 to the power of negative 4 molar. So we have 4.47 times 10 to the power of negative 4 molar over here. How much of calcium hydroxide would be produced from this much of OH minus? Divide by 2, it is 2.23 times 10 to the power of negative 4 molar. Now, how are we going to get the mass? We need to convert it into mole first. So, N equals to mV. This is our formula when we learn concentration measurement, molarity in chapter 1. So the molarity would be 2.23 times 10 to the power of negative 4 multiplied by the volume. Is the volume given? Yes, 0.25 liters. This is molar. So molar is mole per liter, right? So we cross out the liter and we get 5.58 times 10 to the power of negative 5 moles. Now, how are we going to get the mass? Mass N equal to mass over molar mass. What is the molar mass of calcium hydroxide? Molar mass for calcium hydroxide, we have calculated earlier, that is 74.1 gram per mole. So, mass is equals to N times molar mass. So 5.58 times 10 to the power of negative 5 multiplied by 74.1 gram per mole. Okay, this one is mole, so we can cross that out and we are going to get the mass is 4.13 times 10 to the power of negative 3 grams. That is your final answer. Majority of the acids and bases that exist in this world are weak. They ionize partially in aqueous solution. At equilibrium, an aqueous solution of weak acid or weak base contains a mixture of non-ionized acid or base molecule and its conjugate base or acid, respectively. Let's look at example 7.8. The weak acid acetic acid, our vinegar, dissociate in water, and notice that we use the arrow for reversible reaction here. It dissociates partially to produce acetate ion, CH3CO- and hydroxonium ion, H3O+. And weak base ammonia dissociate in water. Partially, it also used the reversible arrow to become NH4+, the ammonium ion, and hydroxide ion. How do we find the concentration of weak acid? First, we write the ionization equation. We can see here Ha dissociate partially in water to form H3O+ and A-. Given C is initial concentration and X is concentration of H3O+ ion dissociated, we use ice table to get the concentration of initial, change, and equilibrium. So we write the Ka expression and substitute X for H3O+ and A- and C minus X as the reactant down here. Assuming that only a small amount of acid dissociate, whereby Ka is very minimal, less than 1. Therefore, C minus X can be assumed as C. It's the same as C because it's very near to C because X is very small. So we replace C minus X with C. And now we can find X, whereby X is the square root of Ka multiplied by C. This is the concentration of H3O+ in the dissociation and ionization equation. An important fact that we have to apply here is the assumption of initial concentration minus X is equals to C, or the initial concentration, can only be used when K or Kb is equals to or less than 10 to the power of negative 4. Let's do example 7.9. The Ka for methanoic acid is 1.8 times 10 to the power of negative 4. So we can assume X is very, very small. Here, if the concentration of the acid is 0.1 molar, initially, calculate the concentration of H plus ion for the X. So the first thing that we need to do is write the dissociation equation. It is partially dissociate to produce H plus and the methanoate ion. So the initial concentration is 0.1 molar. This is not yet available, and this is the change. Negative X, positive X, positive X, and then you have equilibrium. 0.1 minus X, this one is X, this one is X. Now what is the Ka expression? The product is H plus concentration multiplied by the methanoate ion concentration divided by the acid itself, and you're going to get 1.8 there. So insert the values, X times X, okay, this one, divide by this one, 0.1 minus X. This is equals to 1.8 times 10 to the power of negative 4 molar. So just now, we found that 10 to the power of negative 4 can be used to assume X is very, very, very small. So 0.1 minus X is equals to or very near to 0.1. So we put X. We are not going to use this anymore because it's very small. So X to the power of 2, X square, is divided by 0.1 equals to 1.8. So solve this. I have to go here. There's a space a little bit over here. X now is equals to 1.8 times 10 to the power negative 4 multiplied by 0.1 and square root. Now the answer would be, press your calculator, and we got 4.243 times 10 to the power of negative 3 molar. This is the concentration of H plus ion. As we have known, at this column, we try to find X. Okay? Let's find the pH of this acid first. We've known that H plus concentration is calculated to be 4.243 times 10 to the power of negative 3 molar. So if we press the calculator, negative log of this, we're going to get 2.37. Now, if you want to find the concentration of OH minus, we can use POH minus equals to 14 minus pH and find the OH from here. But let's use KW because KW is H plus multiplied by OH minus equals to 1 times 10 to the power negative 14. So this 14 is associated with this lah. Okay, if we put negative log of pH for everybody, here is going to get 14. Right, so this is 4.243 times 10 to the power negative 3. Okay, OH minus equals to this, and you're going to get OH minus is 2.36 times 10 to the power negative 12 molar. That's the concentration of OH minus. The formula to get the degree of ionization alpha is X over C times 100%. This is given at the beginning of this lesson. You have calculated X 4.243 times 10 to the power of negative 3, divide by 0.1, multiply by 100%. So you are going to get 4.243. That is the alpha. How do we find the concentration of weak acid? First, we write the ionization equation. We can see here Ha dissociate partially in water to form H3O plus and A minus. Given C is initial concentration and X is concentration of H3O plus ion dissociated, we use ice table to get the concentration of initial, change, and equilibrium. So we write the Ka expression and substitute X for H3O plus and A minus and C minus X as the reactant down here. Assuming that only a small amount of acid dissociate, whereby Ka is very minimal, less than 1. Therefore, C minus X can be assumed as C. It's the same as C because it's very near to C because X is very small. So we replace C minus X with C. And now we can find X, whereby X is the square root of Ka multiplied by C. This is the concentration of H3O plus in the dissociation and ionization equation. Example 7.10, trimethylamine CH3,3N is a weak base. At 25 degrees Celsius, aqua solution of trimethylamine ionized to 2.3%. Given the initial concentration of it is 0.12 molar, write the ionization equation. Let's write the ionization equation. It's CH3 bracket 3N in aqueous form, ionize in water liquid form to become, this is reversible reaction, CH3 bracket 3NH plus. Okay, we got the H plus from H2O and OH minus. This is aqueous and this is also aqueous. That's the ionization equation. Okay. B, calculate the pH. Okay, the question gave us the other way around from the previous question. So we're going backwards, starting from the formula of degree of dissociation. So 2.3 is X over 0.12 times 100%. So we want to find X, whereby X is the OH minus. So X is equals to 2.3 multiplied by 0.12 divided by 100. That would be 2.76 times 10 to the power of negative 3 molar. Okay, this one, we find the POH first. That would be 2.56. Once we got the POH, we would have pH equals to 14 minus 2.56. That would be 11.45. 4. That's the answer for question B. For C, the question wants us to write KB expression and find the KB value. So we need to write the equation back, and then we use the ice table to get the equilibrium concentration of I change E. So this one is 0.12. This is 0. This is 0. We don't use this because it's liquid, not aqueous. The change would be X. Oh, we already calculated X. X is actually 2.76. So this is minus 2.76 times 10 to the power of negative 3. And this one is plus X. And this one is also plus X. So what is happening here? We need to calculate the final answer of concentration for each species. So this is 0.11724 molar. So what is the KB expression? KB expression is the concentration of the products from the balance equation. Okay. This is divided by the trimethylamine CH3CN. Now, let's insert 2.76 times 10 to the power negative 3, the same concentration, divide by, okay, so the answer is 6.497 times 10 to the power of negative 5 molar. That's your answer. Please do practice 7.2 and practice 7.3 to confirm your understanding on this lesson. We have done all the subtopics in acid and bases. So I hope you have productive time afterwards, calculating the pH of some sort. Alhamdulillah. Thank you very much for your attention. Assalamualaikum.